thanks, John, for the nice introduction, and also thank you for the invitation to present today. So today I'm going to have a talk in two parts. The first part will be more like summer school-like, with like more introductory, and the second part will be more research-like. And the research part is joint work with Kevin Scammon, former postdoc, Adrina Hendricks, current student, and colleagues at Microsoft, Laurent Massoulier, at INRIA, Laurent Massoulier, and Microsoft, Sébastien Bubec, and Neil Tatli. So the setup for today, and I guess you know all about it, otherwise you would not be there. It has lots of data to process, and from industry to science, and we need like automated way of dealing with it. So why I show this slide is because of the series of hypes that we have seen in the last like 10 years. I gave similar talk like 10 years ago for the first part, and I would say big data or data science. But now we say deep learning or AI. Okay, so at the end, there's a series of hypes, but to me, I still do machine learning. And so the reason for the hype, okay, it's very, very classical, is that it does work a bit, in particular for NLP and vision. So this is like work from Jean's lab. This is work from Jean's lab over there. So everything works very well, and the classical reasons for the success is attributed to three factors: a lot of data to learn from, a lot of computers, but overall and above all, a lot of progress and science. Okay, it's not just big computers and big data. It's also like some models. So at the end, if you want to, this will be the only slide where I talk about AI. Okay, so if you get AI only, if you get a mixture of four things, so I've mentioned like algorithm, data, and computing power, but also models, because there is no universal method. And today I'm going to focus on algorithms, okay, keeping in mind that all the rest is very important. Okay, so but I'm an expert in that, so I'm going to present this. All right, so let's go. So this is the outline of the talk. So the first part will be like on optimization for machine learning. And the key aspect here is the fact that when you optimize for machine learning, you optimize the finite sum. And this single like property leads to a lot of nice things. And I'm going to finish this first part by looking at the recent class of techniques that can be quite fast for convex problems. And then the more research part of the talk will be like more recent work, trying to deal with problems where your data are distributed over a network and you want to optimize as fast as you can. Okay, and we'll see like several examples. And the key here, the key message is when you go from one machine to two machines, you want to distribute the fast algorithms, okay, and not the slow ones. And this is a key part of that talk. All right, so let's give the setup. I'm going to consider n observations, classically xi, yi. Xi can be an image, yi can be a label on this image. I have n pairs xi, yi. I'm going to predict y given x based on some function h of x and theta. So x is my input, theta is my parameter, and in all of that talks, the parameter will have dimension d, okay, over there. And so two classical setups. So first, where the money comes from, advertising. So in that case, we have like n is very large, typically 1 billion or more, and the feature vector which is used for those problems is a bunch of zeros and ones. And for every website on the web, then you have a 0 if you have never been there, and 1 if you have been there. Okay, I forgot to mention that n is the number of clients of those search engines. This is you. And given those this navigation history and the ad, they're going to predict if you're going to click on an ad or not. Okay, this is my own web page after I remove ad block, and you see that I get some advertisement for like cultural things for kids, and this indeed I have like small kids, so it does work. Okay, and it works based on a very simple model. The feature vector is very large, phi of x 10 to the 9th, and you just combine linearly all the components of phi of x. Okay, so this is like used a lot in advertising, and also in many areas where you don't have like too much data. Then, and this, in my talk, this will correspond to convex problems, and this is the main focus of the talk. Then you have like other situations, like computer vision, when you want to predict, which is also very useful, like dogs from cats. And so you have a bunch of images, you have a bunch of labels. And here it's not anymore like linear predictions. This is like a nonlinear prediction on X, but the key part, and before, this could be also nonlinear in X in general, okay? But it's linear in the parameter theta. Okay? So the key for convexity is to get linearity in the parameters. But here for neural networks, so you have one linear function, but you have a bunch of like nonlinearities sigma, and I'm sure you have heard a lot of talks about that. And overall, you get a nonlinear function of theta. This is very hard to, harder to optimize and non-convex. Okay? So keep in mind that when you do optimization for machine learning, there are two words, one which is convex for linear predictions, and one which is like non-convex for those types of problems. The way we're going to feed the data is by minimizing the regularized version of the empirical risks. So you're going to take some loss function, L, it can be least squares or logistic. I'm going to show the examples in a minute. And you average over your training data, and you add some regularizer to avoid overfitting. So to make things concrete, you could imagine that you do least squares. Okay, so this is like typical when your output is real valued. But also, if your output is binary, okay, it's very simple, and it typically works quite well. But in the context where yi is -1 or 1, people use the logistic loss, which is of that form. Okay, so it's still convex, but it's more adapted to binary classification. All right, so just to make things concrete, all of that talk will deal with any loss function. It can be least squares or logistic, or if you have like more complex data, okay, like multi-class or structured output, there are convex losses which can be built for those problems as well. So this is the problem, and the key aspect for us is the fact that you can rewrite this problem as a finite sum or a finite average. So here, fi of theta will be about the loss for a single pair of observations, xi, yi, plus the regularizer, and what we want to optimize is a finite average of all this. So now you have two problems that people tackle for those kind of problems. First is pure optimization. I want to minimize this. Okay, I don't really care what if it's going to generalize well. I just want to optimize. So this is the optimization problem. But of course, you want to also deal with testing cost. Okay, so what you want is if I get some new data, okay, coming from the same source as my input data. So now I have to make some assumptions regarding the relationship between my test data and my training data. I want to minimize this, but what I really care about is doing well on the testing cost. Okay, and so I'm not going to deal with this. Okay, so today is only optimization, but keep in mind that what you really care about is statistics, and which is like generalizing well on unseen data. And in one part of the talk, I will mention it again, but I'm going to ignore it for most of it. All right, so this is the setup. So the goal is to minimize this. So now I'm going to review the classical assumptions which are typically made to analyze those problems and the classical algorithms. So first, we're going to assume some regularity property on our functions. So I'm going to assume some form of smoothness. So on the left, a smooth function. Okay, so it looks like nice and smooth. On the right, a non-smooth function. So this is like easy to see in a picture, but you want to put some math behind it. And the most simple assumption that people use in practice is you want the eigenvalues of all of your Hessians to be bounded. Okay, so you take two derivatives and you want all of them to be bounded. And so if you do this for machine learning, where our cost functions are of that form, like an average over the training data of some loss function. So if H is a smooth function, so this could be like a neural network with like a smooth activation, so it can be a linear function. And your L is smooth, then you get a smooth function. Okay, so this is why I typically say this is not a very strong assumption. Okay, so this does not apply for the ReLU. Okay, but anyway, we don't do neural networks anyway, so we don't really care. But you need like smoothness. All right, the one which is like much stronger is convexity. So you look at eigenvalues of the Hessians again, but you want them to be non-negative. Okay, so on the left, convex function, so it goes, it's convex. Okay, And so this is the convexity. And in machine learning, now this becomes a strong assumption because you need to make some assumptions on the prediction function h. And let's focus about that. Oh, before looking at machine learning, sorry. Sometimes we want to do a bit more than convexity. So we want to make sure that the eigenvalues are strictly positive. Okay, so in a picture, this means that in every direction, you're always above your tangents and really above. So if you move away, so this is a function. So this is a tangent over there. So to be convex, you need this to be above that. Okay, and to be strongly convex, you need really to be really above that, and you want to avoid some linear parts like we see over there. So this is like even more convex. And so now you have two numbers. So if you're both like smooth and strongly convex, the eigenvalues of your Hessians are bounded from above by L, from below by mu. And what you get is maybe the most important like concept in optimization, which is a condition number. All right, so you have a ratio of the largest eigenvalues of your Hessians over the smallest. So the ratio has to be bigger than 1. And now if you plot in 2D, okay, so how level sets look like. So this is like in a function in 2D. So every line is a line with an equal value of g. And this is a global minimum, and you move up that way. And when you plot like the level sets for a small condition number, the contour sets look like nice round balls, whereas if you have a large condition number, they look like elongated ellipsoids like this. Okay? And why is it so important? It is important because this will be easy to optimize, and I will show in a picture in a moment, by local descent. Once you are at any given point, the direction of steepest descent tends to push you toward the global minimum. Whereas if you're there, the direction of steepest descent will drive you towards that direction, which is like not super good. Okay, so at the end, if you do gradient descent type techniques, you're going to oscillate a lot over there, and here you're going to go with less oscillations. And the key quantity that will drive and quantify those oscillations are the condition number. Okay, so this is classical if you do linear algebra, and this extends as well to optimization. So in a sense, this is a property of your problem. So if your function is nice, like this, it's going to be easy for us to optimize. If your function is hard, like this, it's going to be hard for us to optimize. And it's the way it is. It's not our fault, okay? It's your problem. It can be easy or hard, and we try to do our best to adapt to it. So some problems are easy, and some problems are hard. And I'm going to present algorithms that will try to do the best they can do, given the easiness or hardness of your problem. All right, so this is convexity and strong convexity. So in terms of machine learning, is it a strong or weak assumption? So it's strong, okay? Why is it strong? Because you need to assume, okay, it is sufficient to assume that you have linear predictions. So again, not linear in the inputs, but linear in the parameters, theta. So if the loss is convex, and all the common losses are convex, like logistic squares or even the hinge loss are convex, but you need linear predictions. Okay, so this is a strong assumption. So why is it still relevant? So first, many problems are still convex. Okay, so like when you have like large features which are binary, typically you use logistic regression. But even if you're not convex, the key of looking at convexity is the fact that it's easier to understand what's happening. So if you have an algorithm which doesn't even work for convex problems, it's hopeless. Okay, so it's always the first thing to look at. What does my algorithm do for convex problems? And another, of course, when you go from non-convex to convex, you lose guarantees about global optimality. Okay, so for most problems, okay, if it works in the convex case, the guarantees will go from global optimality to zero gradient. So most of the things I'm going to present, you could replace distance to the global optimizer by the norm of the gradient. Okay, so typically we use this or that. So theta star is a global optimizer, and you want your estimate to be close to the global optimizer. So this is what we will get if you assume convexity. And what you would get if you assume nothing is something like this. Okay, so this goes to 0. So essentially you tend towards a stationary point. but those stationary points may not be a local minimum or global minimum. Okay? And I think most importantly, and it's important when you use convexity that the algorithm does not need convexity to be defined. If you look at gradient descent, you can run it for any function. You need convexity to analyze it, but not convexity to design it. Later in the talk, when I go over like distributed optimization, I'm going to need convexity for the algorithm, so it's going to be a bit weaker. But it's okay. Let's go. All right, so pop. Okay, so what about strong convexity? So this is even a stronger assumption. Okay, so you need convexity at least. Okay, which I'm going to assume. So linear predictions. But now, if you look at the Hessians of the problem, then you can show that if you take the Hessians of that with that function, you're going to depend on the essentially empirical covariance matrix, which is a D by D matrix, which is like composed of, which is obtained by summing n rank 1 matrices. Hence, the rank has to be less than n. So if you want this to be invertible with all strictly positive eigenvalues, you do need n to be larger than d. Okay, so this means that I have a lot of data. So if d is big, n has to be big. And even if this is true, if you take any regular data set, even if n is bigger than d, if you compute the lowest eigenvalue of the covariance matrix, it is either exactly 0 or very small. And when I say very small, typically 10 to the minus 12. Okay? So typically, the data are naturally do not lead to strong convexity in machine learning, but this has been known for a while, and typically you add some regularizer to make the problem strongly convex. This also avoids overfitting, and in the convex case, this will ensure generalization. But the problem is that since you add some regularizer, you're going to deviate from the global optimum that you're looking at. And so you need the mu here to go down to 0 as you get more data. Okay, so this is like, there's a long list of papers trying to show how small mu needs to be. And typically, this is between like 1 over root n and 1 over n. And so at the end, if you look at, let's say, logistic regression for machine learning, the condition number that we have are between root n and n. Okay, so when n is 1 billion, those problems are really ill-conditioned. Okay, so it's more ill-conditioned as you get more data, and hence this is why it's difficult to solve. All right, so now I have the setup. I have my assumptions. Now I can look at the algorithms that people use. So first, gradient descent. I'm going to assume convexity here to get rates. So convex and smoothness. So gradient descent is very simple. You got it's iterative. You go from step t-1 to step t by going down the negative gradient. Okay, like this. You may do some line search or not. I don't want to go into the details today. And so an example when you have a small condition number, an example when you have a large condition number. And so when you have a small condition number, one step, okay, makes you go very close to the optimum, and then in a few steps, you're very close to the global optimum. Whereas if you have a large condition number, you do some oscillations, okay, and you end up converging, but this may take a while. Okay? So this is what you see in a 2D plot, and this can be characterized like mathematically by providing like convergence rates for those methods. And the distance to optimum measured in function values will go down to 0. So this is what you want. And if, let's look at that bound. So if you are strongly convex, so if the condition number is not too large, then you convert exponentially. So at every time step, you cut down the error by some amount. For example, here, when you go from there to there, I cut down the distance by a big factor. Okay, and if you multiply big factors by big factor, you end up like converging. And what characterizes this convergence is the condition number. So as the condition number kappa gets bigger, this gets much slower. And when the condition number goes to infinity, which is the case when you have like non-strongly convex functions, then this is still valid, okay, but you get 1. So it's just saying that your algorithm is not diverging, so you want a bit more. And the bit more can be characterized. So essentially those oscillations here, okay, this will oscillate more and more, but still converging at a rate which is like slow, 1 over t, but still converging. Okay, so this is why, this is how condition number is essentially characterizing how fast you can go or not. And again, this is not the fault, not the fault, it's not the problem. Some problems are hard, some problems are easy, and it's not the optimizer fault if this is the case, okay? All right, so this is almost optimal, okay? And if you want to get like optimal algorithms, and what do I mean by optimal? So this is like something that optimizer and statisticians like to do a lot. They put some assumptions on a problem, okay, so here complexity and so on, and they say, given those assumptions, what is the best I can do? Okay, what is the best possible performance? And it turns out that this is not optimal. You can do better, and this is a nice work by Nesterov in the 80s, which essentially show that momentum, or a modified version of momentum, will converge. So this is gradient descent, okay, and you add a bit of momentum, which is like the last displacement which you add. So this will slow down oscillation that we have seen in the previous slide. And if you choose the momentum correctly, you can drive, and correctly, there is a formula for it. Okay, I'm not hiding, there's nothing to invent here. You go from condition number here to square root condition number. Okay, so this is very significant. When the condition number is 1 billion, going from there to there, you have a gain of 10 to the 4.5, which is quite significant. And if you just convex, you go from 1 over t to 1 over t squared. Okay, so this is very significant. And in fact, later in the talk, I will show examples of behavior of non-accelerated and accelerated algorithms, and you will see the difference on the simple problem. And now, this is optimal. So again, it's optimal for all algorithms that will access gradients one after the other. And this is a very nice result by Nesterov. So you can't beat this. So in the sense that if your problem is easy, this is the best we can do, and hard is the best we can do. Okay? So this is for any function g. So now let's look. This is what we have. Say a summary of what we have seen so far. We do gradient descent. And then we can if your strongly convex exponential convergence, often called linear convergence for reasons which are a bit mysterious, okay? But if you do optimization, you have to understand that linear is not 1 over t. Linear is this. Okay? And then you could do Newton, okay? So you replace gradient descent, which is essentially going down the negative gradient with a scalar gain by a matrix gain. So this is all nice, so but you have to invert a system at every iteration. This is the negative part. The positive part is that now you get what we call quadratic convergence, so super exponential convergence of the problem. Okay. So if you look from a pure optimization perspective, you may think that why bother about this, which is like called first order, because only accessing gradients. It's first order, but it takes a while to converge because this is 1 over t, for example. Whereas Newton, which is called second order, because you access the Hessians, second order derivatives, is much faster. Okay, so this may look much better, but now if you factor in the cost of every iteration, this is a bit different. Okay, so this is number of iterations. So here I'm doing, this is an operation I'm going to do several times today. So if epsilon is exponential minus t over kappa, this is equivalent to t, if epsilon does this, t bigger than kappa log of 1 over epsilon. Okay? So this is like, you can do the math yourself. Okay? So if I want to achieve precision epsilon, okay, then if I invert this, I get a number of iterations. Okay? So it's proportional to the condition number. Very good. But now if I invert this one, trust me, you get a log-log factor. So essentially, when you do at least locally, once you get close enough to the optimum, Newton will converge in a very small number of iterations. But now if you count the complexity of those iterations, so now I'm going back to machine learning, I'm going to assume G is a finite average of n functions in dimension d. Then the complexity of every iteration for gradient descent is O of nd. Why? I have to compute n gradients. Each of them is of dimension d, so it's O of nd. Whereas for Newton, I have to compute the gradient, O of nd, but also the Hessian. So it's d squared, it's d by d. So O of nd squared to compute the Hessian, and O of d cubed to invert it. So here I'm being like using the simplest algorithm. So at the end, you get like nd versus nd squared plus d cubed. So as soon as d and n are quite big, although this is very small, this will get very large, in the sense that even doing a single iteration of Newton method will not be possible. Okay, so essentially, here I'm describing techniques which are ignorant of the fact that I have averages in my function. And this is very nicely said by a nice paper by Léon Bautou and Olivier Bousquet from like 10 years ago, that machine learning is not optimization. It's a specific optimization problem. And there are three aspects which are very important. The first one is you don't need to go below what we call the statistical error. So what do I mean by that? Is since we optimize an average, so if you average over n functions, typically, if you average like n random variables which are independent, there is a natural standard deviation of 1 over root n. Okay, so your data as is somewhat unknown up to 1 over root n. So trying to optimize below that 1 over root n is kind of useless for testing performance. And 1 over root n is still like not too small. Okay, even when n is 1 billion, 1 over root n is like not so small. Okay, first, you don't need to have a very low epsilon, so maybe this is not really needed. Then cost functions are averages. This is something that we have ignored for the moment. Okay, so I'm going to focus a lot. And I think the most important, and this is what you refer to, Lenka, is you do care about testing error. Okay, so it's nice to do well on the training set, but you don't want to do well on the testing set. Okay, and this is, for this talk, I'm going to assume that this is taken care of by the regularization. Okay, so if you add some regularizer, and typically with lambda being between 1 over n and 1 over root n, you're going to generalize well. Okay, and I will mention this in a moment, that for SGD, you may not need to regularize, but this will come in a moment. So today, the focus will be on that. Okay, what do you do when cost functions are averages? All right, let's look. So let's look at SGD. Okay, so very classical. So I'm going to minimize the finite sum, and since I have a finite sum, SGD here will be SGD with sampling with replacement. I'm going to go down the negative gradient, not of the whole function g, but of a single element, fi of t, I of t being selected at random. And here, with replacement uniformly. Right, so this is the stochastic gradient. So by design, every iteration is O of d instead of O of nd because I select a single gradient, right, assuming that. Okay. Then often you do averaging. Okay, let's not focus about that so much. It's not the topic of the talk. And what you can show for those ones, you can show that the distance to optimum, and now I do have some expectation because my algorithm is randomized. So this is only expectation of my own randomized algorithm. This goes down to 0, but now it's much slower. Okay, so we have moved from 1 over t for convex to 1 over root t, and to exponential to 1 over t. Okay, this is now much slower, but the benefit is that every iteration is much faster. And this is now when you invert this one for the strongly convex case, if you invert epsilon equals kappa over t, you get t, which is kappa over epsilon. So to achieve error epsilon, you just need kappa over epsilon iterations. Okay, and every iteration is O of d. So you see the complexity to achieve a given error epsilon is independent of n, which is something which is desirable. And now I'm going to answer your question. A small nota bene, which is like very important, is that when you do SGD, and if you do a single pass only, so you see every iteration only once, those results are in fact not on the training error, but on the test error. Okay, so a single pass SGD will lead to this on test error, and those bounds are essentially unimprovable. So if you want to focus on test error, then with a single pass, you get this, which is like a bound on test error. The catch is that typically when you do this a single pass, and you tend to underfit. So when t is very, very large, so you have lots of data, then a single pass is enough. But often with a finite amount of data, you still need to do multiple passes. So you end up like starting to minimize the empirical risk, and you need to regularize a bit. Okay, so this, okay, I often give talks on that aspect, but today it's only optimization. So I'm going to assume I regularize not by early stopping, but by adding some regularizer, okay, by adding some mu over 2 times theta square. Okay? So typically mu, either you look for, you do validation to find a mu, or you just take a regular mu, like typically 1 over n is typically good enough. Okay? All right, so this is HGD. So now let's look at what we have at the moment. So we have two types of techniques. We have the stochastic techniques, which are and deterministic techniques. So I want to minimize some finite sum. Okay, over there. This is the example for machine learning, but this is true more generally. I've seen the first techniques I've described are often called batch gradient descent. Okay, I go down the negative gradient of G. Okay, and this negative gradient is a big average. And what I've shown earlier is that you do get like exponential convergence, okay, dictated by the condition number kappa. If you do acceleration, you replace kappa by square root of kappa. But the problem is that whether you accelerate or not, you're going to have every iteration which has a complexity which is linear in n. So when n is 1 billion, every time you access, you want to update your parameter, you have to look at the whole data. So this is very costly. So in a sense, you do very few big iterations. Okay? But you do few big iterations, but every iteration is very costly. Now there is HGD. On the contrary, we'll replace looking at all gradients by a single gradient. And what I've showed is that you replace this exponential of t over kappa by O of kappa over t. Okay, so you lose in the convergence rate, but then you gain in the complexity. It's now independent of n. Now what you have is something like that. Okay, and this plot is important for one thing. So why do you think this plot is important? No. Excuse me? You go up sometimes. Okay, so HGD is the worst possible name ever for that technique. Okay, it's not mine, but when you do HGD, you may go up. Okay, in particular at the beginning, sometimes you go up, and so this is really a key issue about the name. It's not a descent technique. On average, it goes down, but sometimes it may go up. So if you look at plots of HGD, it's not going down all the time. You may go up once in a while, not a lot, but so keep in mind that it's not a descent technique, whereas gradient descent, if the steps are small enough, will always go down. Right? So at the end, you do a lot of iterations, and you end up converging to the global optimum. Okay, in many iterations, many more, but this could be advantageous if you require a low precision. Right, so this is like what we have in a fake plot. Okay, so this is like not a true plot. Okay, so you have time in the x-axis. This is the distance to optimum in logarithmic scale. I'm plotting the deterministic technique in blue and the stochastic ones in green. So I get a line over there. So a line in the semi-log plot. This is essentially exponential convergence. So it's a line for the batch technique, but you see some staircase. Why? Because while I'm reading the data to compute the gradients, I don't do any improvement. Okay, so I spend a lot of time reading gradients, and only after I read all the gradients, I get to do some improvement of my parameter. So I do nothing. I read, I make a big step. I read, I make a big step. Okay? Whereas for stochastic gradient, as soon as I see one observation, I start to make progress, okay? And I make a lot of progress in the first few epochs, and then I get to this 1 over t convergence rate. So if you have 1 over t, and in a semi-log case, you get a logarithm, and this is very slow. Okay? So here, there is no data over there. It's me plotting on the board, but in most, I didn't put them in the slide today. But this is what you see in practice, okay? So in many data sets, you go very fast with stochastic, and you end up like being very slow. So this was a state of the art, like up to, like they said, 6 years ago. And what many people have worked on is trying to get the best of both worlds. Okay, so you want to start as fast as stochastic. Okay, very cheap iterations, but still preserve this linear convergence. Okay, so why you want to do that? Because you converge to, you know that you have converged. The problem with HGD is that should I stop over there, or should I stop over there? Okay, if I stop, okay, I'm shaking, but okay. So let's say if I stop at that level, okay, it's going to be very fast. Sorry. So if I stop at that level, a single pass is enough, but maybe I have not converged enough. But if I try to go a bit below, let's say there, it's going to take forever. Okay? Whereas with faster techniques, you know that, okay, if you do, let's say like 30 passes over the data, then I'm good, and I don't need to optimize anymore. So it's a bit more stable. All right, so let's look at those techniques. So it's called now variance reduction, and the idea is to do to preserve exponential convergence, but with O of D iteration cost. So this started with my postdocs, Nicolas Leroux and Mark Schmidt, and there's a bunch of now other works doing things which are similar. So the way it works is starting from SGD. So this is my SGD recursion, and I'm going to add some terms. And the terms which are added, so they may look weird at the beginning, but so you add some vectors, some average of vectors, and you subtract some other vector. So what are those vectors? Those are stored values of my gradients. So whenever I see a gradient for a given function which I have selected, I store it. Okay, and I call yit the value of gradient I, which is stored at time t. So as I go along, every time step, I select a new function, I of t, compute the gradient, store the value. Okay, so if I have seen this function before, I just replace the old value by the new value. So now at every time step, yit will have some gradients of the function I. Some of them are from very recent, because I have seen that point very recently. Some of them are very non-recent, very old. Right? And this is stored, and if now I am averaging all of my gradients, which I have which I have stored, and I subtract this, it turns out that by doing this, I can reduce the variance of my gradient. So here, essentially, if you look carefully, if you take the expectation over it being the randomness of the choice of my gradient, the expectation over it, this is the full gradient, and this is 0. Okay, so what I have added as 0 expectation, so I preserve the unbiasedness of my gradient, but this is made to reduce the variance. So now I have a much better estimate of my gradient, and really the magic here is the fact that the variance of the gradients goes down to 0 at the same speed as I converge to the global optimum. So this is like a one-line algorithm, and you can show that it does converge. And this is like another summary slide for the first two lines. There's a new result here. So SGD, as I've shown so far, to reach precision epsilon, you need complexity d times kappa being condition number of times 1 over epsilon. If you do gradient descent, you replace 1 over epsilon by the log. This is exponential convergence, but you replace kappa by n times kappa. So when kappa is of order n, you go from n to n squared. This is very, very costly. Whereas with all those variance reduced techniques, you go from n kappa, so you preserve the log, you still exponentially convergence. In the semi-log plot, I get my line that I promised, but you replace the product by a sum. Okay, so you go from n squared. So if kappa is n, which is typical, you go from n squared to n, and hence you get like up to a factor n improvement. Okay, so this is essentially, this is plotted essentially there. Okay, and I'm not going to show the experiments, but you see this also in experiments. All right, so a few comments. This can be accelerated. Okay, because here, if I do Nesterov acceleration, I replace n kappa by n times square root kappa. So when kappa is big, it's a big improvement. And this can be done also for those variance reduced techniques. This is a nice work by Lan, and also nice work by Arshawi and Meral, showing that you can replace n plus kappa by n plus square root of n kappa. Okay, so this is interesting when kappa is very big and even larger than n. No, they are. In fact, those are called often like natural gradient techniques. Okay, and you can, so typically what you do, you accumulate. The problem is that, so if you take the Hessian, Okay, so this is like 1 over n, the sum of the Hessians, like this. So if you take a single one, the expectation is the true one. The problem is that when you do the Newton step, you do inversion like this. And now, if you take the expectation of one of them inverted, is not the correct expectation. So you need to estimate this. You need to accumulate gradients. You need to accumulate Hessians to be able to invert that. And this is essentially what natural gradient is doing. But at the end, you have to invert this. So this is O of, it could be O of D squared. But at NeurIPS this year, we have a paper doing exactly this. So I'll send it to you. Yeah. So this is only, those variance reduced techniques are competitive only for the convex problems. So people have tried to apply it to non-convex, but at the end, people derive some bounds, but they work similarly. So I think people have tried, but there are nice papers by Lombotu showing that it's semi-hopeless, okay, to apply those techniques for CNNs. But it's, and the issue here is what Lenka pointed out, is that this is for training error. And in fact, we have tried to apply this or similar things to neural networks. So you do get a much lower training error much quicker, but then it does generalize worse. Okay, so this is an issue which, yeah, so you really need to have techniques which are dealing with test error, and there's a single one which is SGD. SGD, really, what I meant here, SGD, here, there is naturally like a test error benefit always by using SGD. Okay? But if you do logistic, this is much, much faster. Okay? And, all right, so let's move on to the, to networks. Okay? All right. Pop, pop, pop. Okay, so now I'm going to look at problems where my data are distributed over many machines. So still, I have a finite sum, but it's not the same finite sum anymore. The finite sum I had before was one element of the sum was a single data point or a small mini-batch. Now, every element of the sum will be a whole data set. Imagine you have like several data centers, okay, in New York, San Francisco, Beijing, whatever, and you call Fi the error on that big data set, and you want to combine them all together. Okay, for example, for the data set indexed by I, by Fi, the whole average of many functions. Okay, so this is like the classical distributed setup. So now Fi is big. Okay. And so here I'm going to assume that each of the nodes are positioned in a graph. Okay, so I have like here nine nodes. I have a graph, and I'm only allowed to communicate over the neighbors, towards neighbors in my graph. Okay, so if this is Paris, this is London, then this is whatever Groenland, and this is New York, whatever, and I'm only allowed to communicate to my neighbors. Okay, so this can be either like data centers over the world. This could be like machines within the data center. This could be your core in your multiple cores in your computer. So essentially, I'm going to assume, okay, and this is a model. So real machines are not exactly made like that. But this is what we analyze because it's easy to understand. Is we are constrained to have local communications. So why is it important in practice? Because either you have data which are distributed. Okay, so you have like, if you're Microsoft, which were like our collaborators, you have data in Redmond and in Beijing, and you want to learn a single model for everybody in the world, so you don't want to exchange data. Okay. This could be because you want to be faster, so my data are not too big, but I want to benefit from the computing power of multiple machines. This is more like the classical use. And you may have some legal constraints. Okay, this is very classical for hospitals. People call that federated learning. Okay, you're not allowed to exchange data, but maybe some parameters you're allowed to do it. Well, the goal now is, of course, minimize computation costs. Okay, so this is similar to what I presented before. I want to be as fast as possible, but also now I want to minimize communication time because I may have a finite, like a small bandwidth, and I don't want to wait forever. All right. So first question: why should we care? Should we care should we try to do new algorithms? Why don't we try to distribute classical techniques? So this is what has been done at the beginning. You do like gradient descent, okay, and you can do acceleration if you want. We know from the slides from before that you need those number of iterations to do this. And now I need to compute gradients. Okay, so what do I need? Now I have functions which are spread over that. Okay, I need to compute the full gradient, which is an average of gradients of every local functions. So I need to do like averaging of all gradients over the network. So the first task, if you want to do gradient descent on a network, is how to do averaging of values which are defined locally. So this is the first task when you want to do network optimization is how do I do averaging? So what I will do first is look at techniques to do averaging and then move on to optimization. All right, so what is the problem? So now I'm going very, very far away from optimization now. I have n values. This could be by n gradients. So I put them in dimension 1 because it's easier. I could do the same in dimension d. That would simply be a bit harder to write, but very similar. And I want to average them. So the goal is to compute theta star like that. And a side note, this is in fact the minimizer of an average like this. So in fact, this is the simplest possible like optimization problem you can find on a network. It's average. All right, so you have two types of algorithms when you deal with this. The first is called the first class is called centralized. So you have like it's called like there is the one node. It's called often master-slave network, where one node is telling the others what to do. Okay, the masters tell the other nodes what to do, and the way it is being done, you first start from the network. You first build a spanning tree. Okay, and this you can do with a diameter which is at most twice the original diameter. And then to do averaging, a node calls itself the master, node number 4, and then node number 4 will in the context of gradients, will send the value of the parameters to all of the nodes following the spanning tree. And next step, all the nodes will send back the values of their gradients and averaging along the lines along the tree. And if you do this, at the end, after you get like all the gradients, you get the exact value of the gradient. Okay, and the number of steps you can check the time it takes is diameter because you need to go from there to there. So at the end, you get a diameter number of steps. Okay, and the key is that you have no errors. Okay, so this is distributed averaging. This is like a centralized techniques. One node has to be telling the others what to do on the precise order. And if you do this, so if you do exactly this, you gather gradients at every iteration by getting the exact gradients. This is like the simplest possible algorithm in a network. And what you need square root of kappa gradient step times log of 1 over epsilon. This is number of iterations for Nesterov technique. And you need some communication steps. Okay, since I do one set of communications per gradient step, I multiply by number of gradient steps by the diameter, which is the number of communication steps. And this is very simple. And this is known to be, this was proven by Kevin and other colleagues to be optimal. Optimal in the same sense as Nesterov is optimal. If you're trying to get an algorithm which is going to exchange gradients over a network, you can't beat that. Okay, so this is the optimal possible behavior. But the problem with this is non-robust. Why? Because since you have this centralized algorithm, so if a node goes down, okay, and when you run simulations over a network of size 1,000, one node will go down for sure. Okay, and if you go to 10,000, it's really going to happen. So if a node goes down, then if 6 goes down, then you lose all the contributions from that part of the network. Okay, so this is known to be non-robust. So how you can make it robust? You can make it robust by using what we call centralized, decentralized algorithm, often called like a gossip. So the idea here is that now at every time step, you're going to take a node 4, 4 will call all of its neighbors, okay, receive values of all of its neighbors and average them. Okay? So this is what is going to be done. Node theta I will take averages of other values theta j, and wij is non-zero only when I and j are neighbors. Okay? So you only access the value of your neighbors, and you iterate this, and at the end you do converge to all values have the correct values at the end, the average of all the initial values. All right, so why is it nice? Because you can do those like local steps at different times. You can do them when the network is changing. This is really something which is supposed to be robust. All right, so in terms of math, so I'm going to look at the simplest setup where all nodes exchange values at the same time, and those iterations now become, this becomes a linear iteration. When I go from step t-1 to t, I'm multiplying those values by a matrix W. Okay, this is simply averaging all of my neighbors. For every node, we'll get values from all of their neighbors, and this is getting a matrix like that. So since this is a linear iteration, if I do t steps, I get the power t times the value at the initial point. And the initial point happens to be my initial values, which is a vector of values which I want to average. Okay, so this is a very simple thing to analyze. I have some linear iterations, okay, and to make my life easier, I'm going to use a W is symmetric and doubly stochastic. So it's positive, pointwise positive, and pointwise positive, and summing to 1 for rows and columns. And if I assume this, then it's a classical linear algebra property that the eigenvalues are all between -1 and 1. Okay, the largest will always be 1. Okay, because it's doubly stochastic. And then I have some gap. Okay, and if I call gamma this gap gamma -1, the inverse of gamma is a so-called mixing time of a Markov chain along the graph. So what does it mean? It means that if I exchange information to my neighbors, okay, the time it takes to reach everybody will be the mixing time times some constant. Okay, so this is really a characteristic of the rate at which I'm going to propagate information toward the entire graph. Okay? All right, and so if you have that, since you have a linear iteration, it's known that the convergence is exponential and the rate is essentially the eigengap. Okay, this is very, very classical. So you need essentially 1 over gamma, which is like the condition number for that problem, times log of 1 over epsilon. So let's look how it works in a real problem. Yes. So this is a 2D grid. Okay, so this is a 2D grid. Okay, so I have 100 nodes, and this is the values when I start the algorithm. I want to average all of those values. So now, as I run the algorithm, it should converge to a uniform algorithm at 0, okay? Because this is +1, this is -1, the average is 0. Okay, so let's look at the speed. I hope it works. Okay, so look at the number of iterations. This is pretty slow. Okay. All right. So after 100 steps, okay, so you still like far from being totally uniform. Okay, so you have to imagine that for this to work, you have to do like quite a few iterations. All right. All right, now how can this be used for optimization? So there's a long line of work doing this, coming more from control theory. Okay, a bunch of work, and let's look at what we did. Okay, so first what we did with so Kevin Scammon, Laurent Massoulier, Sébastien Bubec, and Yin Tatley is to try to see what is there a lower bound of complexity. Okay, again, optimizers like to show that things are impossible, okay, or impossible to beat, and we showed that those number of gradient steps and those numbers of communication steps were impossible. Okay, so the key here is to see what are those values. Kappa is a condition number of the problem. It's a pure optimization quantity. It tells me I want to minimize the function. Regardless of having a network or not, this is going to characterize the number of gradient steps. This one is both condition number and mixing time of the graph. This tells me that some graphs will be easier than others. Okay, so graphs with a big mixing time will take more time. And if you do this, you can show that if you just do the stupid algorithm where I'm trying to gossip gradients at every iteration, so I take a gradient step, okay, I try to gossip all the values of the gradients of everybody. This will take quite a while. It's not optimal. So what question is, we have a lower bound, we have a non-matching upper bound. Is there a way to reconcile them? And this is what we have done as well. And for that, this will be the technical part of the talk with some math a bit. We have to go through a dual reformulation. Okay, so here I'm going to assume convexity very strongly, and I'm going to look at the dual problem. Oh, sorry. So this is my problem. I have a finite sum. Okay, I've removed the 1 over n because it was taking too much time. Now, and this is a nice, very simple trick. And this, in this context, this dates back from Jakovetic and colleagues, is that when you want to minimize the finite sum, it is equivalent to assign a different value of theta to all functions. I call that theta I. Okay, function I will have its own value of theta I. But if you want this to be correct, you need to assume that all the theta i's are equal. Okay, so the way to achieve this is simply to assume that whenever ij are neighbors in my network, then the two values have to be equal. So if my network is connected, then this will be equivalent to all the theta i's being equal. Okay, so if this imposes that all theta i's are equal, so now this is equivalent to that. Okay, so this is the first step, which seems trivial, but that will be helpful. Why is this helpful? Now I have a constrained optimization problem. So now I can look at Lagrange duality. So I'm going to add, to create a Lagrange multiplier for all of those constraints. I'm going to call that lambda ij. So I'm going to create the Lagrangian. Okay, this is like I take my constraint and I multiply by the Lagrange multiplier. Okay, so this is the usual like min-max setup. And now I can replace min-mi by max-min. This is where I need like convexity quite a bit. And now, why is it nice to duplicate the theta i's? Now, as a function of theta I, everything is simple. Why? Because theta I only appears in the single fi and appears, okay, by combining several values of lambda I, of lambda ij. So now, if I reformulate, all of that can be seen as a sum of linear functions of all of the theta i's times some combinations of all the lambdas. Okay, that will depend on the graph. So this is like a specific linear function which I don't want to write. But the key is that now all the theta i's are decoupled. Okay, so you see often the case you do Lagrange duality is you want the Lagrangian to be separable, otherwise it's useless. Okay, you want to make things separable, and this is what this is doing. Now you can invert min and max, and now you end up by inverting min and max. This now is separable, so okay, CN soon. Okay, 10 more minutes. And so because this is separable, okay, you can optimize easily. Okay, so you get a sum of functions depending on only on I of various functions of lambda. Okay, so here I'm adding some details, but this is really a key reformulation. I start from my, this is often called the consensus problem, and I end up with something like that. All right. And now what we have done with Kevin and colleagues is simply minimize this one. Okay, so now you can show that this is like a well-behaved function, and we applied simply accelerated gradient descent on that one. And the key aspect, which is not apparent here, but is really the important fact, is the fact that if you do gradient descent over there, you can show that this will do exactly one local gradient step and one communication step. Okay, so this is not apparent. This is really what makes it work. So doing gradient descent on that function can be implemented as a gossip algorithm, and this is what we have done. And if you look now at the math using acceleration, then you get some numbers of gradient step and number of communication steps, and it's a bit late in the day, but it's not optimal now. Okay, and the reason why it is not optimal is because gossip is too slow. Okay, so gossip is very slow, and it's not possible to do good things with the classical gossip. So we're going to need some accelerated gossip, which is something that we have used. So what is accelerated gossip? This is a very nice thing. It's not from us. Okay, so this is regular gossip is a linear iteration. You take powers of W, and so there are several versions. But the key is I'm going to take linear combinations of my iterates. Okay, and if I take a linear combination like this, sum of alpha k times theta k, then since theta k is W power k times c, here I get a polynomial in my matrix. Okay, so this is always the case. This is very general in linear algebra. If I take linear combinations of linear iterations, I get polynomials of my matrix W here. And now I can be smart. I can choose the alpha k, or equivalent to the polynomial, to make this as small as nice as possible. Okay? So this is I can choose a good polynomial. And the beauty is that there is a good polynomial, which is a Chebyshev polynomial. Okay? And if you do this, then not only you get a faster error, okay, it goes faster, and you can do this online. Okay, so this operation can be done. You can update your eta t online, and this is one example of such techniques end up being of that form. Okay, so those algorithms end up combining the classical gossip by some it should be theta t minus 2 over there. Sorry. So you combine. It's some form of momentum where you add, you keep more memory. And now it goes faster. So I've played with my MATLAB yesterday. And it goes faster. You replace, like acceleration, you replace 1 over gamma with 1 over root gamma. Okay? In fact, acceleration can be seen as being exactly the same thing.
So and how is omega t chosen?
So if you give me, the gamma, there are formulas, but they are complicated. There are formulas. There are detailed formulas. And now it goes much faster. Okay, so this is the exact same thing. Okay, two problems, one regular, one accelerated, and pop. Faster, no? Yeah. So you can see after 100 iterations, it's going to stop. This has converged essentially, and this is still like far from convergence. And in fact, I believe this is one of the reasons why when people, okay, maybe I should not say this in front of the camera, but let's do it. So when people use gossip, often when they do like simulations, they take graphs with a very low mixing time, very, very low. Okay, so they find a graph, and for us, we take the grid. The grid is the worst possible, almost the worst possible graph that you can find, okay? Which is, because the mixing time is very large. Typically, it goes up as n or n squared. Okay? So this is really something which is a problem. And if you don't accelerate gossip, you're going to be very slow. And if you don't, you're going to be very fast. Yeah. All right, so then we can do it. Okay, and this is what we have done. This is what we have done with Kevin and colleagues. And now we get to the matching upper and lower bound. All right, so this now is working very well. I will show examples in a minute. But, and this is the most important slide of that part, is when I do machine learning, okay, I don't have special functions. So what I've described so far is a consensus problem, but I've made no assumptions whatsoever on the shape of the local functions. So it could be anything. And my optimality in quotes were only for problems where I don't know anything about the function which I have on the network. But if I do machine learning, I have something like that. So now, what if I take my optimal algorithm and do machine learning? And now I'm going to compare something to something very stupid, which is the very first part of the talk, which is I'm going to put everything in a single machine. So if I start with n machines, each of them having m observations, okay? So this is assuming all the mi's are equal. Then I get a single machine with nm observations. So if I use like variance reduction or any form of acceleration for AGD, this is what I've shown earlier on, okay? And I have zero communication. And now if I use the algorithm from before, which is called MSDA, then I know that I have square root of kappa gradient step, okay, times some communication step. But the problem is that every gradient step, you have to compute the entire gradient, okay? So this means that if m is very large, this is going to be very slow. So what you see, this is the effect that if you go to a single machine to two machines, you're going to be much slower. Okay? So this is very common when you do parallel processing. Sometimes you go from 1 to 2 and you lose a lot. And to recover from losing a lot, I need a lot of machines. Okay? So this is something which is a problem. Okay? You want, when you go from 1 to 2 machines, you want to be at least as fast, okay, and not much slower. And this is what we have done with Adrien and Rix. I'm going to skip the details. And what we have done is to adapt what we did with Kevin to those problems. So now I have finite sums which are distributed over a network. And this is essentially what people need for machine learning. And what he was able to do, to call that ADFS, and to replace this by that. And what you can see is that if you take n equals 1, a single machine, you recover the single machine algorithm. So up to constant factors, things are going well. And it does work, because I have 1 more minute. Okay, so this is like the only like plot with real data. So let's, it's for a grid. So a grid is really like something which is a bit nasty in terms of mixing time. And so if you have a small number of machines, okay, so we are the green, we are the blue, okay, we're France, we are the blue, up over there. And these are the green, Irish, okay, and the green, this is the best single machine algorithm. Okay, so here we see that if you have a small number of machines, this works quite well, okay? Whereas if you go to many machines, then the green gets totally bad and we get totally correct, okay? All right, so this is going to appear at NeurIPS this year. All right, so conclusions, okay, for the distributed algorithms. If you remember a single word, it's really the fact that we should not distribute the slow algorithms, but the fast ones, okay? Otherwise, it's kind of useless. Or you need to be like Google to have like 10,000 of machines, but let's be smart and have fewer machines, but faster algorithms. And yep, all right. Then at the end, so we get like an algorithm which can be, which is good if you have many machines and good if you have a single machine. Extensions, beyond convexity, clearly we're missing that at the moment. We can only take care of convex problems. Is there a lower bound of complexity? In fact, now we have a lower bound of complexity. This is optimal, okay? And Adrien is going to Microsoft to do some experiments on large clouds. Thank you for your attention. I have to finish.